Hello again. We are going to finish or at least complete some more of Chapter 6 in this lecture. Here we're going to look at the R and S system, which actually is a nomenclature system that assigns configuration to each of the two chiral centers in a set of enantiomers, and then allows us to differentiate between those two different spatially oriented molecules in a way that I can designate which one it is that I'm actually referring to. So let us start. And I want to get rid of me. All right. Now, because enantiomers, remember, enantiomers are different compounds. They have to have a different name. I have to be able to differentiate between which spatial arrangement that I am actually referring to. For example, ibuprofen is actually an enantiomer, a pair of enantiomers. I have an active enantiomer, which has this configuration at the chiral center, and I have an inactive enantiomer, which has this configuration. I want to be able to say, this is the one I mean, where this methyl group is pointing out and the hydrogen is pointing behind, where I have the carboxylic acid on this side and the rest of it on that side. Notice those are mirror images of each other. So they are the same compound except for the spatial orientation of groups attached to that chiral carbon. I can use this RS system in order to differentiate between these two enantiomers. The first step in assigning an R or an S configuration is to arrange the groups that are attached to that stereocenter in order of priority. Priority is based on atomic number. The higher the atomic number, right? The higher the atomic number, the higher the priority. So what does that mean? That means if I have an atom attached to the chiral center, the atom that's attached, nitrogen versus oxygen versus sulfur versus chlorine versus bromine versus iodine, I'm increasing in priority. Iodine on this chart has the highest priority because it has the highest atomic number. If I have a carboxylic acid and I want to compare that to an amide, I have a double bond to oxygen. So I have carbon bonded to oxygen, because I count that twice because it's a double bond. And then I have another oxygen, which is my third oxygen. So I actually have, in terms of atomic numbers, I have 888 attached to this carbon. The carbon is 6 atomic number, and then it's attached to 888. Well, this carbon is also 6. I have to be able to differentiate it from my carboxylic acid. I have my doubly bonded oxygen, so I count oxygen twice. And then I have a nitrogen. So this carbon is bonded to the 2 oxygens and then a nitrogen, which has a lower atomic number. So this amide is lower in priority than this carboxylic acid. Same thing here. If I have my carbon and I have my CH2s are all the same, I'm going to look at the next atom that's it's attached to and put those atoms in priority. So when I have both hydrogens, but my carbon is attached to an oxygen, like in that alcohol, that's higher in priority than when my carbon is attached to a nitrogen, like in the amine group, and so on and so forth. So I need to know these priorities for these various common groups, because I'm going to use these priorities to assign the R and the S configuration to my stereocenters. So if two atoms on a stereogenic center are the same, I'm going to assign the priority based on the atomic number of the atoms that are bonded to those attached atoms. One atom of higher atomic number determines the higher priority. So if I look at this compound, here's my chiral center. I have a carbon attached to 3 hydrogens. I have a carbon attached to 2 hydrogens and another carbon, or I have an oxygen, or I have a hydrogen. Well, I know that this is going to be highest because the oxygen versus the carbon, carbon H, is going to be highest priority. I know that my hydrogen is going to be the lowest priority because it has the lowest atomic number. So what I have to do is determine between these two groups, which one is second priority and which one is third. Well, I'm going to look at what's next, right? I have the 2 carbons. This carbon is bonded to 2 hydrogens and 1 carbon. This carbon is bonded to 3 hydrogens. So this is lower priority because that is attached to this carbon. So then I'm going to number them from 1 to 4. So here's some examples. I'm going to assign priority. Here's my stereogenic center. I have bromine, carbon, chlorine, and hydrogen. This iodine is not bonded directly to my chiral center, so it doesn't actually count. Highest priority is the bromine. Second highest priority is the chlorine. Third highest priority is the carbon, and then fourth is the hydrogen. Let's look at this compound. I have my stereogenic center. I have it attached to carbon, 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 carbon. Those are all equivalents. So now I need to figure out what's next. Well, this guy has a hydrogen and 2 carbons. So this has a hydrogen and 2 carbons. This guy has 2 hydrogens and 1 carbon. This guy has 2 hydrogens and 1 carbon. This guy has 3 hydrogens. So this is number 4, it's my lowest priority. This is number 1, it's my highest priority. So now how do I differentiate between this and this? Well, I keep going to the first point of difference. I go CH2, CH3. CH2, CH2, there's another carbon. So this is going to be higher priority than the other one. So my priority is 1, 2, 3, 4. Let's look at this guy. Here I have OH, or I have a CH2O, or I have a C carbonyl. This is going to be a carbon OOH. Oops. Sorry about that. This is what's attached. So this is my low priority because it's a hydrogen. This is my high priority because it's an oxygen. Now this carbon here has 2 oxygens and a 3rd oxygen. So that's going to be higher priority than this guy, which has 2 hydrogens and 1 oxygen. So I have priority 1, priority 2, priority 3, priority 4. This does take some practice in order to get this down. So you need to work with your book, and you want to work at figuring out what these priorities are. So let's do an example. Which of these groups is the highest priority? I have carbon versus carbon. On this carbon, right, I have 2 hydrogens and an oxygen. On this carbon, I have 2 hydrogens and a carbon. That's as far as I need to go. This is higher priority. Here, I have 2 hydrogens and a carbon. Here, I have 2 hydrogens and a nitrogen. That's as far as I need to go. This OH actually has nothing to do with it, because here is my first point of difference between the carbon and the nitrogen. This is the higher priority group. Here I have 2 hydrogens and an oxygen. Here I have 2 hydrogens and a carbon. This is my first point of difference. This doesn't even matter in priority. This is my higher priority. Here I have 2 hydrogens and a nitrogen. Here I have 2 hydrogens and a carbon. This is carbon. Even though I have the oxygens, this is my first point of difference, so this is higher priority. You have to be able to judge which atoms make this distinction, which are counted in the priority system and which are there, but they're really not relevant to what group that's attached to my stereogenic center has higher priority. Okay. So the next step is to assign the R or the S configuration, right? So when I do this, I follow the steps on this slide. I'm going to start with assigning the priority for each group bonded to the stereo center. I'm going to orient the molecule in space so that the lowest priority group is pointing away from you. The 3 other groups are then projecting towards you. So I'm going to have something like this, and then I'm kind of going to have sort of the spokes on a wheel. This is going to be 4, and what I'm counting is those 3. I'm going to read the groups in order from highest to lowest. If my reading, my 1, 2, 3, is clockwise, the configuration is R. If it's counterclockwise, the configuration is S. So if I go this way, which is clockwise, my thing is R. If I go this way, which is counterclockwise, my configuration is S. So let's do a problem. Here are my 2 enantiomers of 2-butanol. What I want to do is assign priorities. So on this carbon, I have an OH, which is the highest priority. I have a carbon attached to a carbon, which is the next highest. I have a methyl group, which is a carbon attached to 3 hydrogen, which is 3rd priority, and then hydrogen is the lowest. So I'm going to orient this so that this hydrogen is pointing back. I'm just going to be looking down at these 3 groups. What I'm going to notice is that when I do this, my groups are connected in that way. I have this clockwise orientation for enantiomer A. So this is going to be an S. Now, the other enantiomer if I look in this direction, I'm gonna go 1, 2, 3, right? This is gonna be counterclockwise. Oh, this is clockwise, which gives me the R. Sorry about that. And this is counterclockwise, which gives me the S. I'm actually going 1, 2, 3, 1, 2, 3. Clockwise is R, counterclockwise is S. So this is going to be the R 2-butanol. This is going to be the S 2-butanol. So clockwise gives me R, counterclockwise gives me S. I'm going to write the R or the S, and I'm going to have that proceed the IUPAC name, and I'm going to put it in a parentheses. So this is the name for that isomer that goes clockwise. Parentheses R-2-butanol. This is the name for the other enantiomer that goes counterclockwise. Parentheses S-2-butanol. So now I have a differentiation. The R and the S is indicating which spatial arrangement I have on that chiral carbon. So drawing these from these names is something that you're going to need to do, and that's actually a little harder than assigning configuration. So the key to this all is the group of lowest priority is going to point away from me, and I'm really going to look at my 1, 2, 3 groups like they're spokes on a steering wheel. Clockwise is going to be R, counterclockwise is going to be S. You need really to make models to do this and become very proficient at it. So here's another example. Let's say my orientation isn't this easy, where this is already pointing in the back. What I need to do is rotate it so that my number 4 goes in the back. So in order to do that, I'm going to rotate it around the axis, and I'm going to put this in the back. This now gives me a counterclockwise, which is the S isomer. Remember, this one is already the way it should be. Actually, this one I have to rotate this way. Sorry about that. I have to rotate this way to get that in the back. And then when I do that, this is going to be clockwise. So that will be R. So sometimes when my lowest priority group is not already in the back, I want to be able to rotate this. The easiest way to do this is with models. If I build this and then I rotate it where 4 is in the back, it's going to be much, much easier. And let me show you what I mean by that using the model that we just had. So let's say I have this group, and let's say yellow is higher priority than the blue, and the purple is number 3. So high priority number 1, priority number 2, priority number 3, and this one is a hydrogen, so this is lowest priority. Well, this isn't an orientation to look at that. But what I have to do is I have to flip it. If I flip it so that this hydrogen is pointing away from you, it's pointing away from you, not me. So when you're reading this, you're going to go this way, right? So if I'm reading this now, I'm going high priority is going clockwise, right? High priority is going clockwise. This would be the R enantiomer. If I have it so I'm looking at it this way, this is still not in the back. So if I build the model, I'm going to rotate it, right? I'm going to rotate it so that when I look at it, I have this image where the hydrogen is in the back, and I'll get the same representation. If I use the other enantiomer, right, where now I have something, here's my lowest priority, I'm going to look at it. If I look at it, now I'm going in the opposite direction, and what I have is the blue is the lowest priority, right? So I'm going in that direction. I think I misread this. If the blue is in the lowest priority, this is going to be S. So this one is S because I'm going from, or the blue, so I have high priority, medium priority, low priority. I go this way, I'm going counterclockwise with the hydrogen facing away from me. This is going to be S. This guy, I'm going to say, okay, my high priority is yellow, next is blue. If I look at it and it's pointing away from you, you're gonna go clockwise, so this is the R. So remember, these are two enantiomers. This will be the R, and this will be the S enantiomer. But the way you're really gonna be sure is to build these models and then look at them. Hopefully I didn't confuse you with that. Okay, so back to the slides. Again, I want to get this so my lowest group is pointing behind, and then I want to connect them. If I go clockwise, well, it's right here, I have R. If I go counterclockwise, I have S. All right, so here's an example. Assign an R or S configuration to each stereo center. The hydrogen is pointing away from me, so basically I just have to look at the circle of those guys. So chlorine is 1, the ethyl group is 2, and the methyl group is 3. When I do this, I'm rotating counterclockwise, so this is going to be, S, right? I'm rotating counterclockwise, so this is going to be S. Here, this is already pointing backwards. If I rotate them, OH is number 1, the carbon-carbon double bond is number 2, because this is carbon attached to carbon, another carbon, and a hydrogen. This is carbon attached to carbon and 2 hydrogens. So this is number 3. When I rotate, I'm going this way, which is R. And that's because the key here is this is pointing backwards. There is a little trick. Let's say I did this and I flip this. So now my chlorine is behind and my hydrogen is pointing backwards or pointing out to me. Well, I still have 1 priority, 2 priority, 3 priority, and I can still make this assignment. This is going counterclockwise, which tells me this is S, right? But because this is pointing towards me, what I'm going to do is I'm going to reverse the configuration. Instead of S, it's actually R. So this drawing is actually equal to the enantiomer of this guy. And again, if you build a model, you'll be able to see that. Conversely, oops, if I drew this guy and I reverse that, here I have the H coming out and I have the OH. I could still do it, that's R, but because this is going behind, I'm going to reverse the configuration, and this is really S, so those two are enantiomers. You may have to build the model. This is sort of a gimmick. If the hydrogen points towards me and it's the lowest priority group, in my wedge and dash, I'm going to assign priority and then reverse it. If the hydrogen is dashed, it points away from me. If the lowest priority group points away from me, I'm going to assign configuration as is. Again, this takes practice. So let's look back at our ibuprofen. This is pointing behind me. It's in the correct orientation. This, remember, is O, O, O. This is H, H, H. And this carbon is carbon, carbon, carbon. So this is first priority, second priority, third priority. Well, I'm going to draw my circle. It's going to be clockwise, which means the inactive is R. This has the same priority, 1, 2, 3, but notice how this is counterclockwise, so the active has the configuration S. So remember, the hydrogen or the lowest priority group must be pointing behind you, and then I can look at it like spokes on a wheel. So here's an example. This is pointing behind me, so this is okay. I have carbon, I have oxygen, I have carbon. This is going to be 1. This hydrogen is going to be 4, pointing behind me. I have carbon with 3 hydrogens, or I have a carbon with 2 hydrogens and a carbon. So this is going to be number 2, and this is going to be 3. I'm going to rotate in this direction. It's clockwise, so this is going to be my R, 2-butanol. Let's look at this guy. Well, nitrogen versus carbon is going to be the first priority. This guy is second, this is third. My hydrogen is pointing away, so it's in the right orientation. This is also clockwise, so this is going to be our alanine. Hopefully this is starting to make sense. And again, if I draw it in my models or if I use models, this is what I'm going to see. When I put that atom, right, that's going behind, and I look at it like spokes on a steering wheel, that is going to help me figure these out and help me go ahead and assign those configurations. All right, at this point, we're going to stop, and then I'll do another lecture where we consider what happens when I have 2 or more stereocenters. I haven't actually talked about that other stereoisomer that's optically active, which is called a diastereomer. We've been talking about those enantiomers, and only when I have 1 chiral center. So in the next lecture, we're going to see what happens when I have two or more stereocenters within the same molecule. So leaving you with that little teaser, I'm going to say goodnight, and I will see you soon.